In this video, I want to go back and talk a little bit more about transformations. So this was your lesson 2 notes, and this is not actually on the notes, but there are a couple things you will probably want to write at the bottom of the notes so that you have those to refer to. So if you will take out your lesson 2 notes and go to the very bottom of the second page, underneath number 17, and we have a couple things we need to write there. I'll tell you when I'm ready for you to write something down. All right, we already looked at several transformations. So already in our lesson 2 notes, we looked at the fact that if you have a negative out here in the front, that is a reflection or a flip over the x-axis, right? So anytime in front of your function you have a negative, you're going to flip the entire function over the x-axis. And we talked about the fact that this number that's on the inside moves your function to the left or to the right, depending on what the number is. And this function that's on the outside of the function, this moves your whole function up or down, again, depending on what the number is. Okay, there are a couple more things that we need to look at as far as transformations go. And in this video, we're going to consider what happens when you have a number here other than just -1, other numbers here in front of the function. You could also have a multiplier here, but we're going to leave that for your pre-cal classes. We are just going to focus on what happens when you have a multiplier right here. Okay, so let's look at our parent function of f of x equals x squared, and we're going to consider what happens if the absolute value of that multiplier is greater than 1. So I'm choosing to say absolute value here because we already know that if it's negative, it's a reflection. So I'm now looking at just the magnitude of the number. How big is it and what does that do? Okay, so we're going to let our parent graph be x squared, and we're going to look at these two functions, 2x squared and 3x squared. So in this function, a is 2, and in this function, a is 3, and we're going to look at what effect multiplying by 2 and 3 have on the graph. Notice that our a here is a multiplier. The other things we've done, the ones that have shifted our function left and right, up and down, those have been added or subtracted. This is what is in the front there as a multiplier, so it's going to work very differently. Okay, so I have typed these functions into our graphing calculator so that you can look at the graph of them and see what is happening. So my parent function that's going to come up first, that's going to be blue, and then my multiplier of 2 will be red, and my multiplier of 3 will be black. Let's see what happens. Okay, so here's the original parent function, that parabola x squared. Here's what happens when you multiply by 2. And here's what happens when you multiply by 3. So as you can see, the function seems to be moving in towards the y-axis. The reason why that is happening is because this is a vertical stretch. Okay, this is what I want you to write underneath number 17. If your absolute value of a is greater than 1, this is a vertical stretch. Okay, and if we stretch it, think about if you took someone, this is impossible, so don't try, but suppose you took someone and you put your hands on their hair and you put your hands on your feet and stretch them. You see how their body mass would get thinner even while they got taller. And so that's what's happening here. Our function is getting taller, and the red one is thinner than the blue one, and the black one is thinner than the red one. And the reason why it's thinner is because it's being stretched upward with a vertical stretch. So when the absolute value of a is greater than 1, we have what we call a vertical stretch. Okay, let's consider a different function. So you can see what happens when it's not just a parabola, but when it's other things. So this one will also be a vertical stretch. Again, you can see the absolute value of a is greater than 1. I'm going to use those same two numbers, 2 and 3, but my parent function is going to change. And so the way this is going to look is going to change also, even though I'm still going to have a vertical stretch. Okay, just as before, I have typed these into the calculator, and you can see our parent function here that's going to be blue. Our vertical stretch of 2 is going to be red, and the vertical stretch of 3 is going to be black. All right, let's see what happens. All right, so here's our original parent function. Here you can see the vertical stretch of 2, and here you can see the vertical stretch of 3. Okay, so again, the vertical stretch makes it taller. It's just that in the last case, as you pulled the function taller, you also pulled it in towards the y-axis. And in this case, we're just kind of pulling up. But we're pulling up by a factor of 2 in the red one, and we're pulling up by a factor of 3 in the blue one. Okay, let's see what happens with this in delta math. So here is a problem in delta math. My parent function is the cube root of x, and I have a multiplier there of 4. So I have a vertical stretch of 4. Now look what's going to happen as I try to work it. If I try to move the green button, that is going to translate the function right and left or up and down. It is not going to be a vertical stretch or what they call a dilation. So I'm going to put it back in its original position. If I want to stretch the graph, I have to pull one of the blue dots. Okay, now look at this one. I have a y value of 1. If I vertically stretch by a factor of 4, that 1 is going to stretch up to 4. So I'm going to move it from 1 to 4. Okay, let me show you that on a different one. Look at this point over here. Do you see the y value is 2? So if I want to vertically stretch this one by 4, 2 times 4 is 8. So I'll need to pull this one straight up to 8. So you can see this one pulled up to 4 and this one pulled up to 8. When you pull one of them, it'll automatically pull all the other ones where they need to be. The important thing to know with delta math is when you are translating a function, right, left, up, or down, you move the green button. When you are dilating, when you are stretching a function, you move the blue one. Okay, let's see what happens now when the absolute value of our number, when the absolute value of our multiplier here in the front is in between 0 and 1. So that means it's going to be either a fraction or a decimal, but the important thing is that that fraction or decimal has a value that is less than 1. So for example, the fraction 2/3 has a value that is less than 1, but the fraction 5/3, that improper fraction, has a value that is greater than 1. So this one would still be a vertical stretch because 5/3 is bigger than 1. I just don't want you to think that every time you have a fraction that it's not going to be a stretch. Stretches are anything bigger than 1. When it's something less than 1 like this, we call that a vertical shrink. Okay, opposite of stretch is shrink. Okay, so let's look on our calculator and let's see what happens when I have a shrink, when I have a value here that is less than 1, but still positive, still greater than 0. Okay, so I've got my parent function in there in y1, and then I've got my two vertical shrinks, 1/2 and 1/3, and I like to put all my fractions in parentheses when I put things in the calculator. That just eliminates a lot of order of operation problems. All right, let's look at what that vertical shrink does to the graph. So here's our parent function in blue. Here's our shrink of 1/2 in red. And here's our shrink of 1/3 in black. So look at what's happening now. It's like the parabola is opening out farther. Basically what we've done is we've smushed it down so that it's now at 1/2 or 1/3 the height that it was before. So again, if you think about our pretend person that we're stretching, now we're going to shrink him and we're going to put our hands in his hair and on his feet and we're going to smush him down and make him half the size that he was before. Well, what's going to happen to his body mass? It's going to go out, just like the red one and the black one went out from the blue one. So it's not that a vertical shrink makes things fatter, it's that a vertical shrink presses things down, which with a parabola like this one, it has the effect of making it fatter, and that's what it looks like. Okay, let's look at a different parent function. All right, now we're back to our square root parent function, and I've typed those in my calculator. And again, you can see I put the 1/2 and the 1/3 in parentheses so that I don't have any problems with order of operations. Well, let's graph and see what happens. So there's our original parent function. There's a vertical shrink of 1/2. And there's a vertical shrink of 1/3. Okay, so again, that vertical shrink, that smushes the graph down. So you can see that this one is not getting wider like the parabola. This one is just getting closer to the x-axis. And that's actually what's happening with the parabola as well. As we smush it down and push it closer to the x-axis, it opens out wider. So it's not that the stretch or the shrink makes it skinny or wide. It's that the stretch or the shrink pulls it up or pushes it down, and that's just what happens on the y-axis. But I think it's a little bit clearer when we look at this square root graph about how it's shrinking down close to the the x-axis. Okay, let's look at what that looks like on Delta Math as well. You guys can see I have a vertical shrink by a factor of 1/2. It's being smushed down to 1/2 the size that it was. Now my parent graph is this exponential function, which you guys probably haven't done a lot with exponentials. Hopefully we'll get to that at the end of this semester. But our exponential function goes up really quickly here. It's kind of flat on this side and it grows really quickly on the right. And what I'm going to do is I'm going to smush this down and make it 1/2 the height that it currently is. So remember that green button? That green button is my translation button, right? That's going to move it up and down, right and left. That is not the stretch or the shrink. So I'm going to hit start over. And the ones I want to look at are the blue ones. So this says 1/2. I want to find a blue one that has a y value that is divisible by 2. All right, so look at this one. This one is at 8. What is 8 divided by 2? Well, 8 divided by 2 is 4. So if I pull this one directly down to 4, not leaving, do you see where it was? It just pulled straight down. It didn't go right or left. Let's do that again. So you can see it's right there on 3, 8, and I'm going to pull it straight down to 3, 4. Okay, I'm not going to move to the right or the left. I'm just going to pull it straight down. So it is now 1/2 the height that it was before. And there's nothing special about this one. I could just as well have done this one. You see it has a y value of 4. 1/2 of 4 is 2. So if I take this one and I pull it straight down to 2, it's going to have the same effect, right? You see how the blue one went to 4, which is right where we had it before. So you can take any one of these that has a y value that is divisible by this number and pull it down to the new y value. Okay, let's do a couple where we look at the transformations. So in this one, I can see that I have a multiplier of 2 and I have a -4 inside the parentheses. Okay, so what is that going to do to the graph of f? Well, the 2 is going to be a vertical stretch by a factor of 2, and that 4 is going to move the graph to the right. Remember, what's in the parentheses does the opposite of what you expect. Okay, same thing with this one. My parent graph is absolute value of x. Let's see what we have here. We have -1/2 absolute value of x minus 4. All right, I want you to think about that negative and the 1/2 as two separate things. The negative is going to be a reflection across the x-axis. And the 1/2, totally separately from that, is going to be a vertical shrink. And that 4 on the outside, that's going to move the graph down. Okay, so don't think about this as -1/2. Think about it as a negative and also a 1/2, because those do two separate things. Okay, so let's look at this one. I've got a parent graph of square root of x. I want to vertically shrink the graph by a factor of 1/3, shift it 4 places to the left and 2 places up. All right, well, a vertical stretch or a shrink is a multiplier in the front. Right and left goes on the inside, and remember, it's the opposite of what you think. Left goes with plus, and 2 places up will be out here on the outside. Make it really clear that that +2 is not inside your square root. When you write these, or when you type these, you want to make very clear that that +2 is on the outside. Okay, how about this one? We're going to reflect, we're going to stretch, and we're going to shift to the right, our parent graph of x to the 4th. So if I'm going to reflect, I need a negative, and if I'm going to stretch, I need a multiplier of 3. Now that shift of 5 places to the right, that's going to go on the inside, and it's going to be the opposite of what you expect.